Now, ESL calculations, again, we first estimate the average daily traffic, and then we fit essentially find from the initial and final traffic, we can come up with then growth factor and growth rate. And then from the growth rate, we can calculate the growth factor, and this is how you calculate the ESLs. This is something most of you already know, so I'm not gonna spend too much time on this. But very quickly, I'll talk about the truck factor, how to get the truck factor. So for the load characterization, we have different tire loads and axles and tire configurations. So this is all the different types of FHWA classification trucks, the trucks that get into different classifications. So all of them, they have different properties. So in ESL calculation or AASHTO 93, we have something called load equivalency factors or truck factors. We use truck factors. So this load equivalency factor is an axle load at any of the axles divided by 18,000 to the power 4. Okay. So they came up with this this relationship. This relationship says that for any axle load, let's say we have 34,000 load, 34,000, or actually in this case it's 17,000 each. But let's say 17,000 in one axle for this particular truck, divided by 18,000 to the power 4 is the relative damage that this axle makes with respect to this standard 18,000 axle truck. So here's an example. For example, if you know the weigh-in motion stations throughout the state will give you gross vehicle weight, the gross weight of the vehicle, gross weight of the vehicle. So, and then typically we use a method to split into different axles. If there's any way you can directly measure the axle loads, that will be better. But we typically split, let's say this total, we have axle load of 17,000 in the front and 22,000 pounds in the back, let's say. So truck factor, because of the first axle, is 17 divided by 18,000 to the power 4, that is 0.8. Axle load for the second is 22 divided by 18 to the power 4. And when you add these up, you would get a truck factor for this particular truck. In a nutshell, this is how we get the truck factors.
Increasing it to the power of 4 is to what? Geometrically increase. It's thought that from experience that it's not a linear relationship, it's kind of a geometric.
Exactly, exactly. So I'm glad you asked, Bill, because we were all, everybody wonders that. Why 4? Why not 3.9 or 3.8? Is it, where does it come? Why not square? How do you know that when you increase the axle load by X much, you would get, when you double the axle load, how do you know that the damage would be like 4 times? We've always wondered that, and my postdoc Mike did, and we knew that this must be accurate because the whole world used this. We did an pavement ME analysis on this very recently. Mechanistic and mechanical pavement design guide. We used the pavement ME software. So we used this, let's say a single truck, and use 18 pounds, and you put 100% of all the trucks in that road is 18,000, let's say. And then we doubled that load, and we doubled load, and then we kept predicting the fatigue cracking using the different axle loads. And then we looked at the ratio of damage between different axles from fatigue cracking perspective. I can explain all that in a long, but push comes, eventually we found that 3.994 or so worked excellent in estimating the fatigue cracking damage because of different axles. So for fatigue cracking, regardless of temperature, see, pavement ME software, you're going to see it includes the temperature fluctuations throughout the year, and it runs a layered elastic analysis. So this number is quite accurate, you know, assuming that pavement ME software is accurate, quite accurate, interestingly. We were expecting it to be not so accurate, but it is quite accurate for fatigue cracking, but not for rutting. We found that for rutting, it's not accurate. But for, you know, when you say damage, what do you mean by damage? If you're talking about fatigue cracking, this is pretty accurate. If you're talking about rutting, you really need axle load distribution done properly. Okay, now, so look at the truck factors. So depending on, for cars, truck factor is very, very low. So we always, we don't use cars. We don't consider cars. Small delivery trucks, they don't cause much damage. Loaded 18-wheeler, they have a truck factor is about 1.135. These are very average numbers. Loaded 40-feet bus is about 1.85 because it has only 2 wheels. That's partially why. This has like, you know, 5 axles. This only has 2. So this, actually, this causes a lot more damage than this one, interestingly. You can see on the pavement, even though this could be loaded a lot more, but this distributes the load much better because it has 5 axles. This has only 3. So it's very important that you calculate the truck factor for each of type of vehicles that you have. Resilient modulus is another very important property that needs to be considered. Resilient modulus is measured using a device that looks like this. It's a triaxial cell. You have a cyclic vertical stress we apply. There's a confined stress. This is like triaxial soil test. So with under confinement. So what we do is we measure the vertical strain, delta C divided by initial height, and we measure the radial strain that will give you the Poisson's ratio of the subgrade and subgrade soil that are used in pavement ME software as well. Resilient modulus is essentially when we look at the deviatoric stress in the resilient modulus device, when we divide that by the resilient strain. So when you run the test, the cyclic, if you run the stress strain, loaded, unloaded, loaded, unloaded, loaded, unloaded, and we have basically hysteresis loops that goes like this. And after a while, loading and unloading gets to a steady state. So the accumulated plastic strain is not considered. So resilient strain is essentially the peak-to-peak strain, just like in the dynamic modulus test. But except here we have a pulse and rest period and pulse and rest period in the resilient modulus. This is a very difficult test to run. Even though there are new equipments out there, you can run it relatively easily, but people don't use this, run this anymore. So important thing is, you know, that resilient modulus gives us the rutting characteristics of the subgrade, and that causes a lot of damage in subgrade. And we have essentially resilient modulus test is run at that expected stresses that in the field. Now, California bearing ratio defined as the comparison between bearing capacity of a material with respect to a well-graded crushed stone characterized by a reference CBR of 100, so 100%. So we actually have a mold of a soil. We have a special load that looks like this. There's an applied load, and there's a standard size plunger, and we have a transducer that measures amount of and penetration of this plunger into the soil sample, and then we measure the bearing capacity by using this CBR is equal to essentially X divided by Y. X is the material load resistance, and Y is the standard pressure used for the reference material. And there's a common relationship between CBR and resilient modulus. This is the most simplest one, 1500 times CBR. There are some other relationships. 2500 times CBR to the power 0.64 is actually a lot more common than this one, even though this looks simpler. But this is also used in pavement ME software. So fair conversion from a CBR to resilient modulus. So we talked about the structural number here. Now, when we look at the drainage coefficient in this structural number, typically have different, depending on the drainage conditions, excellent to poor, very poor condition, and depending on the percentage of time payment is exposed to 100% saturation. So this is depending on the rain levels and all that. So you have to come up with some kind of an estimate of a drainage coefficient for your project, and then that is obviously subjective, but it needs to be based on the knowledge that you have. So reliability is the probability that the pavement system will fail, perform its intended function over its designed life and under conditions encountered during the operation. So essentially, by definition, reliability is the probability of success, or 100 minus the probability of failure. So if you think about like any stress and strength combination, so if these are all the different stresses that you can experience for a given location, for a given, let's say, bottom of the asphalt strain, for example, these are all the numbers that you can experience. If the strength distribution is this, probability failure is essentially in this area. So 100 minus the probability failure is the reliability level. And the reliability level, depending on the, let's say 98% reliability means probability failure of 2%. That's the ZR used in here.
I'm sorry, where does the drainage coefficient go?
It goes to the here in the structural number equation.
It doesn't go in that big block.
No, it doesn't go in there. Big log equation is to calculate the structural number. In a sense, this is what happens. Okay. So from the traffic, you calculate structural number, and from the structural number, you calculate depths and, you calculate depths, but you input drainage coefficients and input. So typically, there are different reliability levels that are recommended for different road types. For very important roads, you have higher urban versus rural. You have higher reliability, you want less probability of failure. For local roads, you might accept a little more probability of failure or less reliability. That's a decision that you need to make. And this portion is serviceability. This is typically with time how the structure of the pavement or how the damage grows in a pavement with time. So this difference, initial serviceability to final serviceability difference, is your amount of deterioration that you expect. So if we do an analogy between pavement ME and this P sub T is your cracking threshold or rutting threshold or IRI threshold. Okay, so this is kind of your threshold. Initial condition, zero cracking, let's say zero rutting, IRI at a certain level here. This is like your final distress threshold. So final distress threshold is increased and decreased depending on different, so that's what people usually do. So what should be the final serviceability